Hey class, today I will be teaching you about greedy algorithms and why you should care about them. We will look specifically at the unweighted interval scheduling problem as an example. This video assumes that you are already familiar with recursive functions in Big O notation, and it might also help to have some familiarity with proof by strong induction. Meet hungry Harold. Harold is very hungry, but fortunately for him, there are a lot of food festivals happening nearby. Unfortunately for him, these food festivals happen to be oddly strict. Because there are so many food festivals nearby, they really do not want to lose out to competitors. If you want to go to a food festival, they require that you go right at the start and stay for the entire duration of the food festival. I know it's weird, but I didn't make the rules. So, Hungry Harold is looking at the schedule of food festivals and is thinking, gee, I'm really hungry. How do I go to the most food festivals? One way we can solve this is by using a use it or lose it recursive algorithm, which will look something like this. If there are no food festivals, Harold can go to no food festivals. This is our base case. Else, Harold can either use the current food festival or lose it. In the use it case, Harold goes to the current food festival and then we recurse on the subproblem with the overlapping food festivals removed. In the lose it case, Harold does not go to the current food festival and then we recurse on the subproblem with the current food festival removed. Out of the two cases, we choose the schedule with more food festivals. Okay, great, we have an algorithm. Let's go take this to Harold. Oh no! What happened to Harold? It seems that our algorithm took so long to run that Harold died of starvation. Let's go back to our algorithm to see what made it so slow. The problem with use it or lose it is that we are essentially evaluating the entire search space of possibilities. For each food festival we encounter, we have to evaluate both the use it and the lose it case, which means that this scales exponentially with the number of food festivals. This algorithm is no good because, as we just saw, Harold will die of starvation before it finishes. So, what is a better way to help hungry Harold get to the most food festivals? Greed. First, I'll give a brief overview of what a greedy algorithm is. A greedy algorithm has three basic steps. First, define the base case. Next, make an optimal first choice. Lastly, recurse on the remaining subproblem. You might be wondering, why is it called a greedy algorithm? The algorithm is greedy because instead of searching the whole space of possibilities, the algorithm always picks the current best choice. Now, let's go through each of these steps. First, we will define the base case. When we have 0 food festivals, Hungry Harold can go to at most 0 food festivals. Pretty straightforward. Next, we will make an optimal first choice. But what does optimal mean? An optimal choice is a choice that is part of an optimal solution. An optimal solution is at least as good as any other solution, or in other words, there does not exist a better solution. Now, I have a few ideas for what our first choice can be. Let's see if they're optimal or not. My first proposal for the first choice is to choose the food festival with the earliest start time. We have to ask ourselves, is this optimal? Before I do any proofs, I'm actually going to try to come up with a counterexample. With a counterexample, we can show that a choice is not optimal. Coming up with a counterexample is a lot easier than coming up with proof, so we should always attempt to come up with counterexamples first. Feel free to pause the video to try this out for yourself. Here's the counterexample I came up with. With my choice of earliest start time, I choose Pizza Party and remove the overlapping food festivals. Now I have one food festival. There are no food festivals remaining, so we are done, and our algorithm outputs a schedule with one food festival. However, we can see that there is a better solution with 2 food festivals. Then, the food festival with the earliest start time was not in an optimal solution, so it is not an optimal first choice. Okay, that didn't work. How about the shortest food festival? Is this optimal? Feel free to pause the video to try to come up with your own counterexample. Here's the counterexample I came up with. With the choice of shortest food festival, I choose Bagel Bash and remove the overlapping food festivals. Now I have one food festival. There are no food festivals remaining, so we are done, and our algorithm outputs a schedule with one food festival. However, we can see that there is a better solution with 2 food festivals. Then, the shortest food festival was not in an optimal solution, so it is not an optimal first choice. Okay, that also didn't work. Let's try again. How about the food festival with the earliest end time? Is this optimal? Feel free to pause the video to try to come up with your own counterexample. I couldn't come up with any counterexamples, so instead, let's try this out on the previous examples to see if they work. In our first example, we first choose Bagel Bash and remove overlapping food festivals. Then we choose Falafel Fett. There are no food festivals remaining, so we are done, and our algorithm outputs a schedule with 2 food festivals. So, the choice of earliest end time works for this example. How about the other example? We choose Pizza Party and remove overlapping food festivals. Then we choose Falafel Fett. There are no food festivals remaining, so we are done, and our algorithm outputs a schedule with 2 food festivals. So it works for this example too. We haven't encountered any counterexamples so far, so let's try it out. Here's a brief recap of our algorithm. In our base case, if there are no food festivals, Hungry Harold does not go to any food festivals. Else, Hungry Harold will go to the food festival with the earliest end time, which I will abbreviate as EET. Then, we will remove the food festivals that overlap with our choice and recurse on the remaining subproblem. This sounds good, but how do we know that our algorithm works? Proof by strong induction. Here's a quick review of proof by strong induction. First, prove the base case. Then, assume the statement is true for all n from 1 to k. Then, show that this implies that the statement is also true for n equals k plus 1. So, we are going to prove that our algorithm produces an optimal solution for n equals 0 food festivals, assume that our algorithm produces an optimal solution for 1 to k festivals, show that this implies our algorithm produces an optimal solution for k plus 1 festivals. As part of this, we have to prove that EET is an optimal choice. First, let's prove the base case. First, we prove the base case for n equals 0 food festivals. If there are no food festivals, then our algorithm will return no food festivals. Then, our algorithm produces an optimal solution for the base case. Pretty straightforward. Next, the inductive step. Assume that our algorithm is optimal for 1 to k food festivals. Now consider n equals k plus 1 food festivals. Let opt be an optimal solution for this problem. So here what I've done is I've just picked an arbitrary optimal solution and called it opt. Consider 2 cases. 1, our choice of EET is part of opt. 2, our choice of EET is not a part of opt. Now let's look at the cases individually. Case 1, our choice is part of opt. If EET is part of opt, then it is part of an optimal solution. Pretty straightforward. Case 2, our choice is not a part of opt. If EET is not a part of opt, then we can replace the earliest food festival in opt with EET to create opt2, which is an equally optimal solution to opt. Then EET is part of an optimal solution. This can sound confusing at first, so let me just explain what this means. Let's say we have the schedule, and our opt solution consists of Bagel Bash and Falafel Fete, which has 2 food festivals. Notably, our choice of EET, which is Pizza Party, is not an opt. What a proof is saying is that we can swap our choice with the earliest food festival in opt to get opt2. In our case, we swap Bagel Bash with Pizza Party to get Pizza Party and Falafel Fete as our opt2. Opt2 has the same number of festivals as opt, so opt2 is also optimal. So why does this replacement work? Here are some key properties. The food festivals in opt do not overlap with each other, and the EET choice ends before the earliest food festival in opt, so it also does not overlap with the other food festivals in opt. That means we can safely swap out the first food festival in opt for EET. Now that we understand why the swap works, let's go back to our proof. To recap our cases. Let opt be an optimal solution for n equals k plus 1 food festivals. In case 1, if EET is an opt, then it isn't an optimal solution. In case 2, if EET is not an opt, we can replace the earliest food festival in opt with EET to create opt2, which is also an optimal solution. In all cases, EET is an optimal solution, so it is an optimal choice. Now we're going to put it all together for the inductive step of this proof. Our first choice, EET, is an optimal choice. For the subproblem of the remaining n less than or equal to k food festivals, our algorithm produces an optimal solution. Therefore, the algorithm also produces an optimal solution for n equals k plus 1 food festivals. Hooray! Our algorithm is correct! But is it fast? Let's do a brief runtime analysis. The expensive operations here are looking for the food festival with the earliest end time and removing the overlapping intervals. To do this, for each recursive call, we must scan the entire list of festivals. Then the runtime of this algorithm is O of n squared, much better than O of 2 to the n. But can we do better? We can do better! If we add a step where we sort the food festivals by the earliest end time before running our algorithm, then we can find the food festival with the earliest end time in constant time, and we only have to scan the list once throughout all function calls, so our algorithm runs in O of n. We still have to take into account the time of sorting, so overall this procedure runs in O of n log n. Hooray for Harold! Earlier he asked, how do I go to the most food festivals? Now he knows. I'll use an earliest end time greedy algorithm. So, why care about greedy algorithms? As we just saw in the case of Hungry Harold, or the official name of this type of problem is the Unweighted Interval Scheduling problem, greedy algorithms can be a huge speed improvement over brute force approaches. We went from O of 2 to the n to O of n log n, which is a huge improvement in time complexity. Why else do we care about greedy algorithms? We just saw greedy algorithms can help us answer questions like, how does Hungry Harold go to the most food festivals? They can also help us answer other questions like, how do I make change with the fewest coins possible? What is the shortest route I can take to run my errands? How do I efficiently schedule my classes? And so much more. Greedy algorithms have a lot of practical everyday uses. I will briefly mention that greedy algorithms cannot be used all the time because sometimes greed doesn't lead to an optimal solution. But when it can be used, greed can be a simple and fast algorithm. Let's summarize what we've learned today. We learned that a greedy algorithm, instead of searching the whole space of possibilities, always picks the current best choice. We learned that the steps of a greedy algorithm are to define the base case, make an optimal first choice, and recurse on the remaining subproblem. An optimal choice means that it is part of an optimal solution, and an optimal solution is at least as good as any other solution. We used proof by strong induction to prove that our greedy algorithm is correct. As part of our proof, we proved that our first choice was optimal. We had two cases, one in which the choice is part of an optimal solution opt. The second case is when the choice is not part of opt, in which case we showed that we can substitute something in opt for our choice to create an equally optimal opt2. Lastly, we learned that we care about greedy algorithms because they are much faster than brute force and can solve many practical problems. Thank you so much for watching, and please, feel free to comment any topics you would like me to cover next, or any feedback for how I can improve my videos. As always, this is your CS Professor of Fun.